Also, thanks for being here despite the very nice weather. So I have really hard competition outside, so thanks for listening. So I will have now a very hard time to explain what I have been doing over the past 25 years in EPFL better than Matthias. He had made an incredibly interesting summary where I learned a lot. And so now I will try to explain the same things in my own simple words. So as you see from the title, there are two concepts that have been a bit kind of at the core of my interests over this long time. It was semantics and self-organization. And what I try to do now is to, first of all, give you a short mini course what I understand by these two words. So what are the concepts? How are they linked together? Then I will try to give an overview of the framework of research that has been mentally a bit my map of what has been happening in my lab. And I have to say it was a lab. You will see there are so many names that show up. So don't think that I'm responsible for all of this. I was just like herding people a lot of the time. And then at the end I will come to some things also for the future, which would be the things I would do probably when I would arrive now and have another 25 years in front. But honestly speaking, fortunately, it's not another 25 years. That would be a bit long at the end. Okay, so first, what is semantics? So semantics is simply understanding the meaning of symbols and how they're related to each other. So here you see two symbols, right? And you give these symbols to a machine. And what does the machine see? It sees two strings of length 6, okay? And then the machine can do things with these strings, can cut them apart, invert them, replace some characters and things like that. That's what a machine sees. If you replace the machine by a person, the person sees something very different. It sees, on the one hand, something to eat, or a cookie is something to eat, obviously. And the other thing, the person will wonder what this is. It must be some identifier, could not say much more than that. If you replace the person by another person, for example, by my wife, Ariane, she will say, "Oh, cookie is my cat, please don't eat." Okay, so this shows, for the other one, she will say that it's just some identifier and so on. So semantics is already, you see, very context dependent, and everyone has also a different semantics of this world. So what has semantics to do with computation? Now, for me, there were always three major questions behind semantics. The first one is kind of the trivial question. So originally, I'm coming from the database community. So before I came to EPFL, I've been working for 10 years, as it has been said, at Fraunhofer, and I was doing essentially database management. And so for a database management person, semantics is simply, I have symbols with some meaning that I want to store and retrieve, right? So you would, for example, take a pair of cookie and some image, and then you can store and retrieve it. Which becomes then very interesting later as we see in a distributed setting. So that's the one question. The second one is that we compute the meaning of symbols. So we want to understand actually, is cookie now food or cat, right? So do we have some basis on which the machine can decide this question? So that's about the semantics. That's the core of the semantics. And then the third one is, why are we using the symbols this way, right? If I'm telling you a cookie is a white cat, you might wonder, is it just a joke, or is it true, or is it false, or whatever? So this is the third big question. And basically, all the research around semantics is revolving around these three questions. So what about computation? So today, if you look at code, maybe someone in the room will challenge me, but I'm just saying it like that. 99% of the code today is imperative programming. In some programming language, people describe step by step of how things need to be done. This can be done very efficiently, right? So you teach first-year students, for example, C, that they learn to use the bytes in a very optimal way and very fast code and so on. But it can become also very complicated. There exists another way of programming, which you might already guess is a way I like a lot. That's fixed-point programming. What is that? It's a declarative form of programming where you basically have some data and some rules. And all that you do is you apply the rules to the data, since nothing new happens anymore. Then you have reached a fixed point. And that's the result of the computation. And this is actually the reformulation of the basics of self-organization. So there's something happening which is organizing by itself just based on the declaration of the problem, and the result comes out by some magic, right? And actually, why I was doing it, you have seen in the introduction the title of my PhD thesis. Honestly speaking, I probably could not reproduce what I did at that time. It would take me some time to get back into that. But at the heart of it was actually fixed-point computation, so some sort of symbolic description of numerical processes in an algebraic framework. And this was under the guidance of Erwin Engeler, whom I visited, by the way, just recently. He's still in good health at his biblical age. It's just a fascinating person. So he said, I mean, just to give you a little bit the setting in which I grew up, I mean, we should not work on supercomputers, we should work on soup computers. And so this is probably, it somehow sticked, and it also stick to me because probably I'm a very lazy person. So I don't want to think about all these details, how to solve the problem. I just want to stir a little bit and get the solution. So that's the two paradigms. Now, why fixed-point programming can be good for semantics? So there are some, let's say, high-level arguments. I mean, you cannot, these are not verifiable axioms, but these are just some general kind of conceptual thoughts. Rules are very modular. You can add and remove rules, and this fits very well the idea that also knowledge is very modular. It evolves, you add new knowledge, you remove knowledge, and so on. Rules can be easily distributed. So, and since semantic knowledge or knowledge is distributed over agents, it's probably a good way to distribute your knowledge in a distributed setting. Rules can also be computed in parallel very easily, which is very practical because you have a possibility to create very scalable systems in that way. Rules have this property of confluence very often. So confluence has a very strict mathematical sense, but it's sometimes also sort of an approximate confluence, which means you can apply the rules in different ways and orders, and at the end, almost always the same or a similar result will come out. So you don't have to care about details. And this basically means that the semantics does not depend on the details of computation. And finally, they are also very tolerant to incompleteness. So basically, if some rule is missing, the computation will go on. Probably some results will simply not be produced. Of course, all of these are more or less true in different settings, but this is kind of the general thinking. Now, there is one more aspect in fixed-point computation, which seems to be even more important, and that's the notion of emergence. So in many cases, you design rule systems, and then you do this soup computing, right? And you have already the desired result in mind. So that's something that I did in a former life when I did query optimization. So you could build query optimizers where you give basically an original query, some rules, how you can transform it to equivalent queries. You just apply these rules, so you stir, and then you have all possible plans, and then you can evaluate them. So that was very fashionable rule-based query optimization. But there exists another way that is emergent, that the rules converge to something that you don't know, that simply is not known in advance. And that's not really a bug, but it's really a feature, because it is basically a mechanism to explore semantics where the meaning is previously not fixed or known. And it's just the result of interactions at the end of the day. And so this is, of course, what attracted a lot of my attention. And we'll come back to that later again. And fixed-point inference is just then to discover what is this structure that is emerging that you did not know in the beginning, and this is self-organizing, it doesn't require central control, so it had all these desired features. And so applying this computational paradigm to our three main questions is solving very specific problems that we can identify. So for the how question, so the rules can basically organize the computational substrate. So that can be many things, but in networks it's the organization of a network, for example, based on the patterns that are governed by semantics. And you will see in a minute why this is important. Then they can reason about meaning and do in local inferences and aggregate basically some global semantic structure. And finally, they can also be used to basically argue about what is the meaning of the symbols, why are they here, are they good or bad, all these pragmatic issues that we have in the real life. And I would want just now to go through each of these three questions. And I will just present you a very simple idea. It's this kind of always the kind of the initial idea that has been starting the whole thinking process. And then I will show you just a glimpse of what came out at the end. And so NCR mix was already mentioned. And so I was asked in 2001, basically when I arrived, oh, make a talk, right? And so say something about it. Probably really had the same problem. So what I did is what I could do best at the time. I made some sort of an architecture of a system, and it's not important what the details are. It never materialized that way, obviously. And then as a second afterthought, I attached this small box to the architecture because I thought if it's distributed, we need some sort of way to find the data in the network, right? And so this was then the data access structure. And honestly speaking, I do not know exactly at which stage of development of the idea I was when I was putting this slide, but probably the slide was starting the thinking. That's my theory today. And so the problem is that if you have a decentralized infrastructure, and peer-to-peer systems have already mentioned, so at that time people liked to find music files in the net, and that was of course a highly illegal activity, so it was good to hide it. So people searched for this, and so basically it was a pair of a music name and some music file. And so that was a popular problem at the time. So many people were looking at this, and there were solutions that were called distributed hash tables. So they're distributed, they hash, and they're tables. And you see the names here. And as the name says, the very first thing they do, they hash the name, right? So they make out of cookie some meaningless symbol. Now this is, has some advantages, but it has one problem. If I want to find now all names that start with cookie, that's impossible, because on the hashed values I cannot do that anymore. So fortunately I did not hear about those, because what would have happened if I heard about those? I would also first hashed the names, right, obviously. Now, and that's often in research, it's a bit of a dilemma, right? You need to know what is happening, but if you know too much, you're kind of limiting the space in which you can think, right? And sometimes it's good not to know too much, and then you find other ways that others have not thought about. So what is the problem with this hashing? So we all know that names follow a zip distribution. What does that mean? There are very many names that are very rare, and there are a few names that are very popular. Now, if you distribute the names on nodes, the nodes that receive the popular names are poor, right? Because they have to manage many names, right? So that is without hashing. And that's why the people built distributed hash tables. They destroyed basically this order, and then everyone got a little bit of the same meaningless names. And so I searched for this figure here for a good zip, and in French in addition, and I was stumbling over Mandelbrot. Everyone knows, I guess, Mandelbrot, which is Mandelbrot sets. I had the pleasure to meet him at ETHC when I was a PhD. And actually, he is a very good example of the power of fixed-point computation, because this set that is this fractal structure is defined by one line of equation, essentially. So a very simple line. If you look at this line, you will never imagine what comes out, right? And this comes out. Okay. Now, what happened next is quickly said. I draw other diagrams of that kind, and I thought about how to connect them together. And then it turned out that you can build actually overlays by keeping the order, but you just have to make sure that, so to say, in the regions with many names, there are also many, at that time we called them peers, that manage them. Today you call them agents or whatever. And now the problem is, of course, if you organize this way, you have to assure that you find them also fast. And if you would now go in database balance, you would build an index tree that is highly unbalanced, the search cost would explode because you have to traverse a very long tree. But by wiring nicely this, you can avoid it, and you get the nice logarithmic search costs. So this was the starting point of a long story. And it's not only to imagine, so this was the known target structure. So this is an example of fixed point computation where you know what you want at the end. But you can organize this as a process. And this process, this is a simplified explanation, but basically the peers would meet each other. They would study each other, when they manage the same kind of names, they would study, oh, how do we have a lot of names here? And then they decide, yeah, we have a lot, so let's split and make a tree a little bit deeper here. And so in this way, naturally, the tree would grow. And so it's clearly a fixed point process. So this was the starting point then of a long story of at least 9 different PhDs that studied then all aspects of how to generalize this structure, how to apply it to information retrieval, how to make the storage safe. Then, of course, at some point, some of my PhD students thought that this period is really old-fashioned. We have to invent new types of structures and so on. So it was a long story. I will not read all the names because I'm probably already over time here. But it's close to my heart to also show all the people who have graduated from the lab, because that's probably the most important thing that we are doing here. But then there was this other box in this Terminode, and so there was another line of work which evolved out of this other box, and that was a following observation. We saw then that people were buying sensors, including us. When we bought the camera sensors, I got immediately a call from Central. Why do you need so many cameras? Are you monitoring our students or whatever? So no, it's just for an experiment. And then they built an infrastructure to collect this sensor data, to process it, to query it, to share it with other nodes, and so on. And we saw many solutions to that, right? So it was like everyone in the web would build their own web server to publish a web page, right? So this sounded extremely inefficient to me. So this started then the thesis of Ali, who built what's called the global sensor net architecture. So this was really an engineering, how to design a system where sensor nodes can communicate in a decentralized way. And this was really very interesting work and got this Test of Time awards a long time later, so they were really late. Okay. And then again, there were lots of other projects that were dealing more with sensor data management, moving into cloud data management, but always driven a bit by the same idea. How can we build efficient infrastructure to share data in a distributed environment? Okay, so that is a little bit the story of the how. Now the story of the what, where did this start from? I can show you here a picture that was given to me from Mike Brody, I don't know when, it was probably 2000 something. He was CTO of Verizon, and he said, okay, yeah, you see, that's our real problem. We have 10,000 databases that are all connected and they need to talk to each other, and we're spending most of our time connecting them, right? Yeah, this looked to me very much also like a peer-to-peer network. So at that time, I was very much on these peer-to-peer networks, and I was kind of eating every type of problem that is related to that. And I think he was also on this famous first audit panel, right, as far as I remember. And so let's simplify this a little bit. So what does that mean? So we have data stored in many places, and people use different names, right? So semantics is about names and what they mean. And so here we have names for people and for organizations. And now, thanks to ChatGPT, I can do this in Chinese, and I can pretend I understand Chinese. But for the machine, all of this looks like Chinese in any case. And so computing the meaning in this context means essentially to understand which names correspond to which names. Right? It's a simple name matching game. And so there is one way that, and that was probably a way that makes it so painful for CTOs, is that you have a global data manager administrator that makes then the mappings. And then the semantic web came and they say you have to annotate all your names with our ontology. Could also solve the problem, but it's a very centralized way of approaching the problem. So the more decentralized view it would be to say, okay, so now there's kind of local administrators and they have a specific problem, so they will study this other database and then they will connect it and understand what is the mapping of names. And so step by step, more and more of these name connections would occur. And okay, and there exist even tools. So this is a tool that we had then, of course, European projects on that and so on. This is a tool that could establish these local matchings. Now looking at this, okay, these tools are pretty nice. They study the two schemas, they look at them, think about them, and then they come up with some proposal. But they only know about these two schemas. Now, if you look at this setting, now this is my exercise of today. My last lecture has an exercise. Here are two mappings, C1 and C2. And by looking very carefully and for some while on it, you might easily discover which is the correct one, C1 or C2. Okay, now you have the solution in your mind, and it's obviously C1, right? If it were C2, you would have proven that the name of a person is the same thing as the name of a company, which is, of course, a totally useless discovery, right? So this simple observation just tells you one thing. The network as a whole has more knowledge than each of these individual mappings. And this gave them the idea of a lot of thinking, how could we exploit this, and ended up then in one of the theses. That's probably the only thesis that got the EPFL thesis award in my lab. And there were not so many from IC because it's kind of, we are not discovering black holes or new quantum particles. And the idea was simply to kind of translate this into structure, mathematical structure, a vector graph, in which basically probabilities are computed by sending back and forth the current probability estimates. So essentially, it is nothing else than a fixed point inference. So there I was very happy because, again, we have solved the problem simply by the same paradigm. Then this went on. So here just mentioning another work by Hung. He got also some Best Paper Award for this. And so, of course, sometimes the network has not all the information. So one idea was, could we imply the human in the loop? And if doing so, how can we basically ask the right questions? So this is active learning. So you identify, so use the same methods that you use to kind of fix the errors in the network. You use to select the best candidates to ask questions. So you fix the errors faster. And we could show that this works actually with real data, which is for data integration projects quite surprising because such data is extremely hard to get. And this work on semantics went also on, and there were then different ways of looking at the problem, and we moved more and more also towards information extraction. So how can we extract structure from distributed types of information, which can be either some activities of the user, or it can be directly the text. So, for example, Surrender, he won some award by extracting entities from tweets. But what I liked much more was the title of his paper, which was When Apples and Blackberries Were Only Fruits. I think this is just a great title for a paper. And then Amit, he built basically very similar ideas as we use in data integration, some very nice methods to extract taxonomies from text corpora, right? Something normally people do by hand. He just had the idea, we throw in the text and we get out the taxonomy, and guess what, it worked. Without latest AI. Then there was also a lot of work that started in semantics and sensor data. So Xi Xiang, he was a student actually that came over from Stefano's lab when he retired. So that is, and he made very nice work by making a layered architecture, how to create higher and higher semantic extractions from sensor data. This was then leading finally to another Test of Time award. And then there was a lot of work also studying semantics and sensor data from different perspectives in the context of smart energy. We had a project on smart energy, on mobile phones, on time series. So, you cannot only stick to one problem, right? You have to give a little bit room to people to move. So this was the story about the what, and then the why. So the why, that was a problem also that was strongly motivated by peer-to-peer systems, because you could not only download at that time MP3 files, you could also download viruses. And this was not such a good thing. And then you could download actually files from some police organization that is hunting you. That's even worse. And that's, the problem is, I'm meeting a stranger and I do not know whether I can trust, which means, can I cooperate and we both make a gain? Will he defect and I make a loss and he makes even much more gain? So that's a real problem. And actually, I have to mention one person, Jean-Claude Dusigné from the University of Lausanne. He's an economist, that he pushed me on this topic. I mean, up to that point, trust was kind of something related to security and cryptography. And he cleared my mind that this has nothing to do with that. That's just a tool. Trust is really about how people believe. And of course, today everyone knows this. And by the way, this is also something that general society should study a little bit more. Now, you can build systems. So this is just a hypothetical systems, like similar like PageRank for web search, where you say, okay, we compute the reputation by saying what people say about other people, but at the same time factoring in how much we trust them, which is, of course, a fixed point inference. But that's, of course, a little bit a simplistic view, so then we started to look about a bit more detailed on the problem and discovered that, of course, trust is not the same as trust. There's one thing to trust that I get from you the right file. It's another thing to trust that you tell something about someone else which is correct. And the third thing to say, I have stored what someone else has said about him, and I give you the right information. So there are different contexts of trust. And so that led to some work, and curiously, one of these papers got then, for some reason, the highest cited paper. So since 25 years, people still cite it. I don't know why. It was not so fantastic, honestly speaking, but okay. Probably the title was good. And now, that was, but there was a good thesis coming out of it. Zoran has been working, among other things, also on this. And then, of course, these problems are always like ping pong between measures and countermeasures. Of course, once you have put into place these reputation-based systems, people become smarter, they start to do strategic behaviors, then you have to say, okay, we have to be a little bit harsher with those that cheat. It's not only that we don't work with them, we kick them out of the system. Then, of course, the people have the idea, oh, that's not bad, I take a new identity, I come back in and do the same bad things, so they have to make a price on exiting the system. So this leads to very complex game theoretic questions that Hung has been then investigating in his thesis. Okay, now then we have worked on this, but then, so around 2010, 13, social networks came up, and we discovered that not only peer-to-peer networks are a dangerous place, social networks are even more so. They're spreading misinformation, they're polarizing. Do you want to hear about the chocolate diet? Yes. That's my favorite story. So, actually, what happened there, people wrote a scientific article, totally fake, without the LLM, by the way, by hand still, that proved that people who eat chocolate lose weight, right? And then this was published in some B or C journal, and then it was taken up by some journalist, and then it made it to the social media, and people started seriously to discuss chocolate diets. Okay, do you remember No Billag? So this was 2018 vote on whether we should pay for television or not. And there was a very polarized discussion in Switzerland, but interestingly, we analyzed this on Twitter, and you see the two poles are very different in nature. I leave it to your imagination what the one is and what the other is in the political landscape of Switzerland. I do not interpret this further. Okay. Anyway, so this observation then made us to look into more seriously into how to detect misinformation. So first we tried the usual thing. We tried machine learning. That was part of Alexandra's work. And there, it turned out to be very hard. It kind of worked, but it depended strongly on the availability of training data, which was extremely scarce for this type of thing. Then Tam said, okay, yeah, let's do something else. We look at these disinformation labeling sites like Snopes, where journalists essentially say this is fake and this is true. But this is a lot of work. So we could help with some machine learning to give them the articles where we learn the fastest about what is fake and what is not fake. And in that way, basically, he could show that this would really accelerate this work, so save real work. Jeremy looked then at another thing. So he studied basically which newspapers are publishing on which events, okay? And he used some recommender systems methods to kind of organize the newspapers by kind of similarity of publishing patterns. And one pattern was, of course, by geography. It's logical that a newspaper in India is more on Indian events and in the US more on US events. But he discovered a second thing which was totally unexpected, that he could discover basically the big publishing conglomerates in the world, which means essentially the information is controlled by them. He could even show if one buys a newspaper from another, the pattern moves towards the buyer's pattern, essentially. So that's a very interesting discovery. And then Panayotis, he looked at this chocolate problem. So basically, he wanted to see, can we find the provenance of the information, right? So if I see this tweet, maybe where does this come from? I have to find probably a newspaper article. Once I find this newspaper article, how do I find the scientific article? So and this is entered then into complex technical questions, but then also in natural language processing. So he was probably one of the first users of some of these early AI-based models or predecessors of those, and built a very nice solution to tackle the problem. And then, of course, the kind of the brother of trust is privacy. So trust is about can I believe the information I receive, and privacy is can I believe that others do the right thing with my information, right? And so people in my group started also to work on this. So in social networks, for sensors, for health, that's where the blockchain, by the way, otherwise I was not involved with blockchain. This is just a very isolated thing. And Julia worked actually, she's from Ukraine, and she worked on activism and how to understand how campaigns on the internet evolved. That was also like very interesting work. And in this privacy domain, I have to still point out Hamza. So he was really working on something great in the sense that he had an enormous impact. So what he did, he took this long 300 pages of privacy policy published by all these platforms who no one ever reads, and built a tool to basically read them automatically to identify which are the key clauses in it. So this was, at that time, it's 2018, so we're still light years away from usable LLMs. This made it to the press. He got all kinds of prizes, Swiss Security Thesis Award, and all kinds of things. So it was really super impactful. And what was behind is indeed sort of a very simple precursor of LLMs, but he used still a lot of training data that was very expensive to acquire because this means to hire lawyers and so on. So you see, these are the practical issues that you have to deal with. And, but it kind of worked very reliably for this specific problem. Which brings me to my large chapters. So these days you cannot talk without mentioning about two things. The one thing I will not mention, but the other thing, LLMs, I'm going to mention. And if you don't know what the first one is, we can make later a survey, and I guess the result will be clear. It's large language models. Okay. Of course, I programmed already during my PhD neural networks, and the biggest mistake in my life was probably to say, oh, these do not really work well, I do something else, right? Nowadays, we have these LLMs. Now, those who are experts, like Antoine, he will afterwards tell me, oh, it's not exactly like that, right? But I think it's almost like that, right? So when you're training an LLM, what is happening essentially, the data that you feed, this is the text that you use, is the rules in reality that tell the system how to adapt the network. Okay, and the rules are all independent. You shoot one after the other. That's called stochastic gradient descent. And the network starts to converge. It's not tested for convergence, but it stabilizes in a sense. And so it's really pretty much in the same spirit of how these LLMs are being trained. So it is a supercomputer, and it has the magic that at some point, when you made them large enough, magically understanding emerged, right? So this model seemed to understand things. So what was the impact of that? First of all my latest PhD students worked only on LLMs. And Angelika, you will be the last in the line, right? Title is not yet fixed. But please finish by that. That was the first one. And the second one is that some problems that we consider to be very hard in terms of data semantics become kind of almost trivial. So this is basically, Rudy mentioned kindly Linkalong, my startup, which probably continues to exist. And what it does, essentially, it does, in a nutshell, 4 steps. It takes data, social media, so that's where it came from. So we wanted to automate social media analytics. And we wanted to do that for organizations like ICRC, later on WHO, and so on. And so we extract facts. So that's information extraction. Then we take these facts. Of course, we get the same facts many times, so we have to do some data integration. So we have to consolidate the facts. Once we've consolidated the facts, we ask the user a question. So the user can now ask the question in natural language and not in some absurd programming style. And so then the query is generated and executed, and then the result is summarized. So this pipeline, that is kind of now the standard pipeline, has four research problems, former research problems, I would say: information extraction, data integration, natural language to query translation. I did not do that, but I had a number of master projects in industry where people tried to solve this problem, and summarization. I checked, each of those has easily more than 5,000 to 10,000 publications on the web, right? And now it's a commodity, essentially. It just works. Simplified, but for practical purposes, we can say that. And so this makes us, of course, think what is our role, right? So if understanding of text, at least, the what has become a commodity, and even methods to do it kind of no more needed because LLMs kind of generally can do that, that will probably not be the most important problem to remain, probably. They are simply solved by this magic. The question of why, yeah. So now the people have not to think how to find the answer to the question, but they have initially find the question, right? And in my practical life, when I talk to people working with link-along, which are people in the real world, I have always to ask, what is your question? Right? And that's often a very embarrassing question, because I do not exactly know what the question is, right? And so that is why a wise guy like Einstein apparently has said, I spent in 1 hour 55 minutes on finding the right question, and only 5 minutes for the solution. And if you look now what are the typical job profiles that you find, it is about what's called prompt engineering, right? I remember in my lab meetings, I wanted to push my students to do prompt engineering. And they said, what is this? I mean, I will not play around with text, right? I play around with networks. But okay, everyone can make sometimes a mistake. I did neural networks myself. And now it's a job skill, basically. But I think it will also change, more importantly, the way we think, because our brain will be occupied much more by thinking about questions and trying to find solutions. Right? So it's like people have forgotten to do multiplication of large numbers in their head, right? It's simply a skill that is not needed anymore. And what about the how? Now, this is very nice, because today the database community, where I'm originally from, gets kind of marginalized by the AI and machine learning community. If you look, the size of conferences are one order of size different. But I think in the future this is going to change. Either the big AI/ML conferences will become like database conferences, because they will have to deal with the resource management to make these solutions more efficient, less resource consuming, and able to deal with large data sets, right, that go beyond some size of a text window. Now this is my not so surprising probably prediction. Now, what is about agentic AI? Because we are not talking anymore about AI now, we are talking about agentic AI. And if I look at current agentic AI, it looks pretty much like this workflow that I have shown. You have some agents that are put together in some controlled manner, and then everyone does something. And now I'm coming back to my so beloved peer-to-peer systems. You could also imagine systems that were agents, which are now not stupid software programs, probably with a human behind, but agents are very smart software programs that can do a lot of things that even humans are not capable to do, start to self-organize. So they could start to discuss among each other who does what, right? So like we did with peer-to-peer overlays, just the task is maybe way more complex. They could exhibit unexpected semantic behaviors, and there have been experiments that show if you let them talk to each other, they quickly develop languages that humans do not understand anymore. And we need probably to monitor them a little bit, right? Do we trust these agents, what they are doing, right? Without we understanding exactly what they are doing. And this is an interesting question, because will the why actually stay under our control? Because think about it. We can control, right? But control will kill the evolution. Self-organization leads to evolution. Or we cannot control, and there will be some emergence, and then we don't know whether this emergence is exactly aligned with what we are interested in. So that's the dilemma that we will have, and that's how I want to end. Shall we trust the process in the future? And now, that's the end of my talk. I have still to acknowledge many people. So I mentioned, I think, all my PhDs. But the PhDs worked not alone. They worked in a group. I had very, very capable postdocs. For example, Manfred is here. He's now managing a group that has about 30 times the size of my largest group size. And many, many others who did a great job in running projects. I mean, there have been infinite numbers of projects. I cannot spend 25 million on my own. And so they made really the group living. I wanted also to acknowledge colleagues. So many of the PhDs had the privilege to work not only with me, so they could work with some other colleague of mine who helped them in many ways. So I really appreciate it anytime. I wanted to thank all the IC staff. As we all know, and Rudy always likes to emphasize, the most efficient staff at EPFL. So thanks a lot, and particularly also in the past years now in the section. I mean, it's like the director is just here to say yes, right? And the staff says, oh, we have to do this and that. And yes, very perfect, sounds good, okay. I wanted also to thank the central staff. Now, that's a very contentious topic because we have, of course, this tendency to complain about the central staff because they burden us with all kinds of administrative things. But they have also to deal with many burdens, and I lived that through my vice presidency, that there is also real complexity there. And then finally, I want to thank the most important person in my lab. Here you are. Chantal. So I have to still tell you how she came to me, right? I have to tell this story, so that will become. I'm the only professor at EPFL that was not nominated at the meeting of an ETH council. Did you know? I got a very embarrassed call by Badu at the time, because it was the same meeting where Aberer was nominated. And we didn't never come to the point nominations anymore. So I was nominated by email afterwards, okay? But even better, then I inherited Chantal. That was kind of the compensation. And she stayed 25 years in the lab. And this was really extremely good experience. Thank you very much.
Thank you so much, Karl, for this wonderful journey through your research life. We have time for a few questions, and we have some microphones for you to post them.
I told you, questions is always the most difficult.
The first question should come from your family. They never had.
So the usual problem at a conference is you had an amazing talk and nobody asks a question, which means everyone is totally confused, or you did the best job imaginable to explain everything and there are no open questions. Well, coming back into a French-speaking environment today, and having lost all my French, I have a superficial question. Ariane, Chantal, everybody else who is a French native speaker, how much meaning is Karl making of speaking French, when he speaks French? So is the semantics that Karl speaks okay? So
25 years is enough.
If you rate it between 0 and 100%, where is he now?
I had really great teachers in French, right?
Okay.
Chantal and then Ariane, and it was
So
perfect.
You're doing a good job.
Yeah.
Any other questions?
So Karl, great talk. I don't disagree with how you framed LLMs
Oh, thank you.
at a high level.
Now I feel relieved. I mean, here are the experts.
I do, one thing I found interesting was just the progression of the topics you've worked on that does, I think, give you a fairly unique view on what the risks are that are coming next. And so you left us with this question at the end. How are we going to be able to trust LLMs that can self-organize in a way that we can't necessarily measure? But I want to hear your first answer on that as well, not just be posed the question.
Of course, I cannot answer this question for you, but I have sort of a hope. I hope that some fantastic things will happen. Maybe we'll discover things that we humans could not think about. And I hope that not bad things are going to happen, right? Because things can go also wrong. And I think probably that is one of our challenges now. If we decide, and I would so say it like that. I mean, we can make a law that says never ever let AI agents interact in an autonomous fashion among themselves and give them in the same time some button that can do some harm, right? That we can do by law, which means that definitely some people will do it immediately after, right? So we probably rather think about how we can avoid that too bad things are going to happen. But probably that is something I will try myself to let agents start to talk to themselves. Just like, should not be very difficult to do, right, with everything we have today, because even the coding you can ask the agent, please agent code a system of agents that talk to each other, and you run.
I think I saw a plot to that movie, which I think is conveniently also called Transformers, so I think it could work out that way.
So it's more of a comment, like on the first slide you mentioned it's 99% of the code is imperative. I think it's a bit harsh, given all the things, LLMs, all those kind of things, so that seems to be improving.
Well, LLMs for me at the moment is not code, but it's becoming.
But it's being used
becoming the code now,
as a replacement for code.
Now let's say up to recent.
Yeah. And there's like a lot of business rules, all those kind of things, constraint programming, all those kind of things. So there's maybe.
I checked it. The probably correct number is 80 to 90%, and the 10% are kind of declarative specifications that are circulated.
And what I really like at the end, you mentioned about asking questions. So what I see in my company is actually asking the right questions, not even knowing what the solution is or what the objective is. And by asking questions, you actually discover in the space, and you figure out what your objective is and what your solution is.
That I can only confirm. I think that's the way, but that's the way we start to change our thinking, right? We will become question generation and answer analysis machines instead of analysis producing machines.
Good, so we now get to the most formal part. For this we need a VIP. Today we'll have even more. First we have VMIPs, okay, very many important people. And Chantal, can I please ask you to organize that?
So now comes the surprise part.
The purveyor of, the official purveyor of honorary degrees, as one of his many functions, Ed Bignot, please.
Thank you. So my job is to do the formal part, and for this I have two pieces of equipment, and they go hand in hand. I'll explain why. But before that, where's Karl? Karl. Yeah, so thank you for the great talk. It's fascinating. And, you know, the last class that I've taught recently, and I'm not teaching this semester and for a while, is around computer security. And we try to teach third-year students the confused deputy problem. That involves humans and computers. And I wish the best of luck to Matthias, who will be teaching, and whoever will be teaching this class in the future, when we will have to teach the confused deputy problem between computers, agents, and humans, because God knows where this goes, right? It's my pleasure and honor to give you the honorary degree. This is an important tradition that we have at EPFL. When you don't retire, you get promoted by decision of the Comité du Corps Enseignant to a new title, and it is my obligation to read the promotion document to the laureate. For this, I, of course, need my glasses because there are a few important parameters you have to understand. One is this is written in a font that the person that receives the document with absolute guarantee will not be able to read themselves without that piece of equipment. That actually happens to be the case for vice presidents as well. The second thing you have to understand is that it has to be by law only one sentence. And the third thing you have to understand is it is in French. So I'll read it in French. Alors, cher Karl, now I can't see you, but I can read. L'École polytechnique fédérale de Lausanne, sur proposition de la conférence du corps enseignant, décerne le titre de professeur honoraire à Monsieur le professeur Karl Aberer, en reconnaissance pour ses contributions scientifiques exceptionnelles dans les domaines de la gestion des données, des systèmes distribués et des systèmes mobiles d'information et de communication. Point virgule. Pour son rôle pionnier dans les technologies pour la confiance numérique et les systèmes pair à pair, point virgule, pour son engagement indéfectible au service de l'institution, notamment en tant que directeur du Centre national suisse pour les systèmes mobiles d'information et de communication, that is MIX, et vice-président pour les systèmes d'information, point virgule, ainsi que pour ses apports à l'innovation et à l'entrepreneuriat illustrés par la cofondation de la société Linkalong et sa participation au sein du Conseil suisse de la science et de l'innovation à l'EPFL le 1er septembre 2025. Félicitations.